Anybody have bonus question turn in or no? No? You do? Okay. What? Yes. All right, you ready? The train's going to move fast today. So today we're doing 7.2, and I think we're going to try and squeeze some 7.3 in here as well. The idea, I started to show you at the end of class last time, this idea of volumes. So before we begin, there's some preliminary stuff here that I want to make sure we're all comfortable with. By the way, these notes are all on Canvas. You can get to all this, all right? So I don't expect that you copy every little thing down here. First, we all should be comfortable with what the volume of a box is, right? Actually, the technical word for this is a parallelepiped. Okay, so you get a three-dimensional box. If you know the length, the width, and the height, then you can calculate the volume, right? The next thing we need to be comfortable with is the volume of a right cylinder. So if we have a cylinder, we call it a right cylinder because you could have something that looks like this, like a cylinder that's been kind of like tilted over. That would not be a right cylinder. A right cylinder, this angle right here is 90 degrees. So like a soda can, all right? So the volume of a right cylinder is pi r squared times h. So again, these are things we should all be just okay with, right? Nobody objects, right? We have that. We have the height. We have the radius, r. Then the volume of this is pi r squared times the height. There's one little thing about this I want to point out. Pi r squared is the area of a circle, right? So you can look at this volume formula as being, basically we're taking the area of that top surface and we're multiplying it times how deep this thing is. And that will give you the total volume, okay? No objections? All right, so the next object that we need to be comfortable with is a right cylinder that we've drilled out the center of it. So imagine that we take, I'm gonna show you here in a second, but I want to draw it. Let's say we take a right cylinder, and then we come through and we drill out the center. So we drill out a smaller cylinder right through here. Right? Like toilet paper, yeah, sure. Okay, so we've drilled out this hole, right? And we want to know what is the volume of this. Now, to do this, we need a couple of things. We need to know the height, right? We need to know the height of this. And then there are two radii. There's the smaller radius, and then there's the larger radius, right? So I'm going to call the radius that goes from the center out here, I'm going to call that R out, the outer radius. And then the radius of the smaller one would go from here to here. That would be your R, I'm going to call that in. So that's the inner radius and the outer radius, right? So what we can imagine doing here is really just first, this volume, right, should be equal to the volume of the bigger one without taking anything out of it, and then subtract from it the volume of the smaller one, right? If we do that, that should be the volume of what's left if we drill this out. Make sense? So the volume of this one is what? What's the volume of that? Pi r squared. Pi what r? R out squared, right? R out squared times h. And then we subtract from that the volume of this one, which would be what? Pi r in squared times h. Right? That all make sense to you? Yeah, so there's some things that these have in common, right? These both have a pi, these both have an h, so let's factor those out. And so if I factor those out, I'm going to write it up here. This volume, right, will be, I'll write it on top. This volume would be, let's pull out that pi, let's pull out the h, and then what I would have here is r out minus r in, squared, right? Those squared. That's what I get if I factor out a pi and an h from both of those, right? So that's what's in the notes here, all right? It says if you have Now, my picture's a little different. My picture, it's the same thing, right? But I just happen to use a very small h. So if this h is really small, then it's going to look like that, not like this, right? And this we will call a washer, because it looks like a washer, right? If you've ever seen nuts and bolts and washers, right? So this is a washer. And you can see the formula here. I have the pi pulled out. I put the h in the back. I did that for a reason. You'll see in a minute. So you have pi and h have been pulled out. Then you have the outer radius squared minus the inner radius squared. No complaints? Everyone's comfortable with that? All right, let's begin with this, all right? And we're going to start developing the idea, and then I'll get to, there's another formula we're going to need to agree on. So in Canvas, right, if you go to Canvas and you go to our course files, under files, under course notes, there's something here. It says chapter 7.2 and 7.3 volume summary, all right? It's going to be a summary of basically everything I develop here on the board. So you don't need to copy all my pictures down. It's all going to be here for you, but I think it's important for us to go through the construction rather than me just throwing everything up here for you and showing you a picture. This is what it is, though. This is the actual notes. If you download that file, this is what it is. So as I draw this on the board, just know you're going to be able to go back and look at this, all right? Okay, with that said, I'm going to turn this projector off here. Okay, I'm going to turn this off. We'll refer to that. I need the whole board. And you know what? I'll do it before I turn it off. The whole goal here is this. I mentioned this last class. The whole idea here is that we were able to find the area, right, between two curves. That's what 7.1 was about. It's finding that area. And so what we want to do today is we want to take that region bounded by those two curves. Imagine it's in three-dimensional space instead of on a flat sheet of paper. And we want to take it and wrap it around the x-axis. So we're just going to take that region, sweep it through around the x-axis like this, right? And when we do that, we're going to create a solid shape, right? That's what's going to happen as we swing it through and around the x-axis. And that solid shape has a volume to it, right? And we want to know what that volume is. I'm going to make it somewhat transparent so you can see the inside. You see the inside is not a straight cylinder, right? It curves up and goes back down. That's because the lower function was not straight, right? It was curved. So we want to know, what's the volume of this really odd shape, right? Seem like a reasonable thing to want to know? Yeah? Okay. So let's try it. How are we going to go about this, right? That's the question. How are we going to attack this? We're going to need the integral, right? That's the main thing. We need the integral. Come on, stop. There we go. So what I'm about to show you is what we call volumes of solids of revolution. All right, of revolution, like wrapping, not like a revolution, right? But we want to wrap something around an axis. We want to know the volume of that solid, all right? And there's two methods to do this. There's what's called the method of washers and the method of shells. We're going to start with washers. Okay, so method of washers. All right, now before we get into the method of washers, do you remember when we were doing areas? Sometimes when we were doing areas, sometimes your rectangles were vertical and sometimes they were horizontal, right? When we were doing areas in 7.1. They were vertical when they were functions of x, right? That's when you would use vertical rectangles. And when you had functions of y, you would turn your rectangles horizontally and you would use, instead of top and bottom, you would do right and left, right? We have something similar with washers. And I'm going to tell you what it is now, and it's not going to make sense until I do some examples. So the method of washers, we want to use this when our rectangles are perpendicular. I'm just going to put perp if that's okay with you. Perpendicular to the axis of rotation. All right? Again, that's not going to make a whole lot of sense right now, but as we do more examples, that'll make more sense. All right? So let's just start with just the general picture. We have, I think I'll start fresh over here. We have some function here on top. Let's call this top one here f. Okay? That is a function of x, yes? I'll call f of x then. And then we have some other function below it. They don't need to intersect, but I will make them intersect just for this example. That's g of x, right? And I think after 7.1, after last class, everyone should be able to understand, or should understand the idea of how we'd get the area of that region, right? But now what I want to do is I want to take that region and I want to wrap it around the x-axis, and I want to figure out what that volume is. Now that's going to be pretty hard for me to draw, right? Because it's three-dimensional. I'm trying to draw it on a flat sheet of paper. But I'm going to at least start with something, right? So I'm going to label here my x-axis a little. It's like two arrows that are curved. You see this? Two little curved arrows like that? That's showing where my axis of rotation is. Because later on, we're going to do, our axis of rotation may not be the x-axis. It actually might be somewhere else. So for now, if I'm putting this, that means I'm going to wrap this around the x-axis, and I'd like to know the volume. So what we're going to do is exactly what we were doing before when we were trying to find areas. We're going to imagine cutting this into an infinite number of vertical rectangles, right? But instead of adding up the area of each of these rectangles, right? Instead of doing this, A to B, let's say this is A, this is B. Instead of doing this, remember this was, I told you, this was the height of the rectangle times the width of the rectangle, right? Instead of doing that, we don't want to do that because that would just give us area, right? This formula is not going to work. We need some formula that's going to somehow create that solid shape. So I'm going to imagine taking just that rectangle, just that single rectangle, and wrapping it around the x-axis. And can you imagine what that shape would look like?
A washer.
A washer, right? It would look like a washer. So I'm going to come over here to the side, and I'm going to, I did this with areas when we were doing 7.1. I'm going to draw the x-axis again. There's my x-axis. I'm going to draw my little rotation. I'm going to draw my rectangle here. I'm going to label the top of the rectangle with the blue. I know you don't have colors, okay, so we can just put F there. And then the bottom of the rectangle would be the G function, right? And that would be no matter where the rectangle is, right? No matter where it is, it would always be the blue on top, red on the bottom, right? So if we wrap that around the x-axis, imagine wrapping that. I'm going to try and draw it to scale here. If I wrap that around the x-axis, I'm going to get something that looks kind of like this, right? That's not really centered. That should be up a little bit. Let me move it, because my axis of rotation is right here. So it should be maybe something like this. We don't have to be perfect with this. The main idea is that we have a washer, right? You'll see it? So what it comes down to now is this. It's very simple if you just back up and just take a look. When we wanted the area, we found a formula for the area of one of these, and then we added them up with the integral. So if I want to wrap this whole thing around the x-axis, I'm just going to find the formula for the volume of one washer and then add them up with the integral. So we need to figure out what the volume of this is. All right, so what is the volume? What is the volume of that slice? I'm just going to call it a slice because it's only one piece, right? What's the volume of that slice? Well, we just talked about what the volume of a washer was a second ago, right? The volume was, we pulled the pi and the h out, and then we had r out squared minus r in squared, right? That's what it was? That was the formula we just all agreed on. No one disagreed with me. The only difference here is that our washer's turned up instead of laying down, right? It's just vertical, but it's still a washer. So can you tell me what the outer radius is?
Integral plus whatever is left between, like the bottom, like g of x and then the x-axis.
So I'm saying on this picture, on this washer, what is the distance from the center to that top edge, right? From here to here, that right there is r out, isn't it? That's your outer radius? And what is it for us? What dictates that? What?
Area under f of x?
Not area, not area. Just f of x, right? It's just the function's value. Whatever f is, right, at that point, right? Whatever f is at that point, this top blue function is what dictates what that outer radius is going to be, right? So as I move from left to right, the outer radius will be controlled by f, right? So that's just f of x, right? This is just whatever f of x is. And then what's the inner radius? G of x, right? The distance from here to here, right? The distance, I'm gonna put it this way. The distance from here to here, that's g of x. That's your inner radius, right? That's this right here. So if you want, you could, if it makes it a little easier for you, if this is our rectangle right here, right? Here's our rectangle right in here, right? And it has the blue is the top, so that's from here to here is f of x, and then the bottom one is the red, right? Yes?
On this, is that also the axis of rotation on the washer?
Mm-hmm. The axis of rotation is this right here. Yes. Okay, so I know what the inner radius is, don't I? I know what the outer radius is. The only thing I don't know is h. What's the thickness of this washer? dx, right? Wasn't that what we were doing when we had, when we were trying to do areas, the width was dx, right? Same thing here. dx is how wide this is. So the width of this, h, I guess we'll call it, right? This right here, h, is dx. So the volume should be pi times dx times the outer radius, which is f of x, but squared, right? Minus the inner radius, which is g of x, but squared. Do y'all see it all? Pi h, outer radius squared, minus inner radius squared. That's the volume of one slice. Now I'm going to rearrange this. I'm going to put the pi in front. I'm going to do f of x squared minus g of x squared, and then I'm going to put the dx on the back. And the reason I'm putting the dx on the back is because we're about to add all these up, right? And to add them up, we use the integral. So do you believe that if that's the volume of one slice, then the volume of the whole thing should be the integral? So we're going to add them all up, right? From a to b. Now when I say from a to b, that means my rectangle, right? Remember, this distance from here to here to my rectangle, that's x. And I'm going to let that x go between, well, start at a and go to b, right? Move across. We're going to add up all these washers, right? All these like infinitesimally thin washers. We're going to add them all up. And that should give us the volume. So we have pi. And then we have the f of x, right, whatever that is squared, minus the g of x, whatever that is squared, and then dx. And that is our first version of the master formula for finding the volume of a solid of a revolution around the x-axis. Does anyone have any questions about the formula?
Can we put pi out in front?
Yes, pi could come out front, absolutely. Was that your question as well? Yeah. The pi is a constant, so it can come out front. Any other questions about it? All right. I want you to I want to go back and look at one picture right here. This one right here. I want to look at this again, just by itself, because there's something about this that I think is going to be important. Well, I know is going to be important. If you look at it a certain way, it'll make your life a lot easier. So we have this picture here. We have our axis of rotation, right? That's the axis of rotation right there. And then we have this rectangle here. And we have this distance, or this function on top was the f, and on the bottom was the g, right? Everybody here agree with the idea that the distance from here to here is r out? Yes? And the distance from here to here is r in, right? And in this particular case, the distance from the axis of rotation to that blue thing, right, is just f of x. And the distance from the axis of rotation to the red thing is just g of x. But I want you to look at it slightly different. I want you to look at the outer radius. Okay? I want you to look at that as the distance from axis of rotation to the outer edge of the rectangle. Okay? The distance. So I like to look at it kind of like this from this perspective. Let's say that you're a person and you're standing on the axis of rotation. We're looking down. That's my head, okay? That's my head. I'm standing there. And so imagine me standing here on the axis of rotation. And then on the ground, I've got this rectangle laid out in front of me, okay? This rectangle. If I were to get a tape measure and measure from me to the outer edge, right? From me to this outer edge, that's what R out's always going to be. It's not always going to be just a function, as you'll see in a moment. Sometimes it's just the function, sometimes it's not. So look at it more of like a measurement of a distance. And then what about R in? It's the same, right? Except one little change in the words. This right here is the distance from axis of rotation to inner edge of the rectangle. So in that sheet that I said is on Canvas right here, this one, nope, not that one. Where is it? Wrong one. Well, I thought I just oh, there it is. There we go. Look at my formula that I have in that box. Do you see the difference between that formula and the one that's on the board in the box here? Yeah, so instead of me saying f of x, it's not always going to be f of x. It's always going to be the distance from the axis of rotation to the outer edge of the rectangle. So in my formula, I don't call it f of x, I call it r, capital R sub O, so outer radius. And then capital R sub I is inner radius. And I think in the notes I do state what those are. Let me see. On the side here, it should say it. Yeah, it says it right over here. R0 is the distance from the axis of rotation to the outer edge of the rectangle. Ri is the distance from the axis of rotation to the inner edge of the rectangle. All right? Any questions? We're going to do our first example. Let's just keep it pretty simple for this first one. All right. The region bounded by y equals x squared, y equals the square root of x, is rotated about the x-axis. Find the volume of the solid generated. Okay, that's it. So we've got this region, it's bounded by these two curves. We'll take that region, I'm going to rotate it about the x-axis. I want to find the volume of the solid that's generated when I do that. So what I'm going to do is I'm going to start drawing the picture of what's going on here. First, I need to know what the graphs look like, right? So y equals x squared is our parabola. It's this one. And you know what? To match colors, I'm going to change this to a red. To match what we have over here. Sorry. Because that's going to be the one on the bottom. So this is x squared. I thought someone moved that closer to the, oh, it's a little, perspective was off there. It was a good shot. Who moved that? Someone? Who moved that? Was that you, Austin? All right, next function, square root of x. Looks like that. Okay. So what we've got, right? Do y'all see the region bounded by the two? Yeah, it's this little tiny little region in here, right? So I'm going to take that and rotate it around the x-axis. So does it make sense to use the vertical rectangle in there? I mean, do we have the same curve on top and bottom if we move that rectangle back and forth? Yeah? Okay, so imagine I have a little rectangle in here. I'm going to be wrapping that around the x-axis, right? So let me draw for you that little circle. And then over here, I'm going to take some time to draw my x-axis. I'm going to kind of exaggerate things over here so you can see it. I have the blue curve on top, right? That's what y equals square root of x up there, right? Then I have the red one on the bottom. And then that one is y equals x squared. So the two things I need to know to use the formula are the outer radius and the inner radius, right? So imagine you're standing on the axis of rotation, right? Here you are, standing here looking out, and you want to know your outer radius, distance from you to the outer edge of the rectangle. That's this right here, right? What is it? It's just the square root of x. For this problem, it's just the square root of x, right? So I'm going to go RO. I'm going to follow that is square root of x. And then the RN would be this one right here, right? It's getting a little tight here on the board, sorry. Rn would be the x squared, yeah? Yes?
So you said that we're doing this when we're using a vertical triangle.
Vertical rectangle, uh-huh.
Yeah. Will we be doing the same for one horizontal?
Yes, so if I would ask you to wrap this around the y-axis instead of the x-axis, then you would want your rectangles to be this way. But then these two would need to be functions of functions of y, not functions of x. So we'll get there. We'll get there. Any questions? We're there, right? We just used the formula now.
You need your intersection, please.
Oh, we need intersection. Thank you. Yes, we'll need our A and B. I'll move that. Yeah, so we need to know where these hit each other. And I think I'll skip that step because it's somewhat trivial where these hit each other. Right, they hit at 0, and then here, I think just by inspection you can tell if you just plug in 1, You get their intersection. You could also set them equal to each other and solve, but that's more tedious. So I think I'm ready. The volume of this will be equal to pi. So in my formula, notice I pulled a pi out. So pi integral from 0 to 1, and then I have something in here dx. So what goes first? R out squared, right? R out squared. R out for us was the square root of x, so square root of x, that's going to get squared. And then minus the r in, which is the x squared, but that's going to get squared. And those are going to be easy to square, right? So pi integral 0 to 1. Square root of x squared is just x, and then x squared squared is x to the 4th dx. And now that should be something that you look at and be like, no problem, right? Antiderivative of each of these. I think we can take this one the whole way, yeah? So the antiderivative now, bring the pi for the ride. 1/2 x squared minus 1/5 x to the 5th. That's your antiderivative. Evaluating that fundamental theorem of calculus, 0 to 1, right? And when you plug in 1, let's see, 1 into that, then you have to plug in 0. Wait, when you plug in 0, it's just 0, isn't it? Yeah. It just kills everything off, so that doesn't really matter. Over here, though, you get pi. If I plug in 1 here and 1 here, I should just get 1/2 minus 1/5. That's 3/10. 3/10 pi. 3/10 pi. Would be the volume of that solid if you were to take that region and wrap it around the x-axis. Now the units, we don't have units, okay, because we don't have any measurements here, but if this was measured in, let's say, feet, right, then we would say cubic feet or something like that. Yes?
Is that just like the rectangle part or the whole, like the shape?
That's this whole thing. That's this whole region wrapped around the x-axis. Whatever that looks like, it's hard to draw it, right? But it's whatever that is, that's the volume of it. Yeah, the volume of just the rectangle